बात करें गुड मॉर्निंग बोल दो.
Good afternoon, students. Today, in the lecture series of abstract algebra, our topic is maximal ideal. Myself, Dr. Govind Sharma, Assistant Professor Mathematics. So, the learning object of to understand the properties of maximal ideal, to know about ideals, and to understand the properties of ideals. In this in this lecture, we study about the maximal ideal and properties of prime ideals also. So we are going to start our lecture. Then we continue with quiz. First, what is the meaning of ideal? Basically, ideal is a subring of R. Let S be a subring of R. Then it may be ideal if it follows some property like first A minus P belongs to S, and if S is element of S and R is the element of R, so SR is equal to R. There, this is right ideal, this is left ideal. Third, the if subring is called ideal if it follows the cancellation. Now we move to maximal ideal. What is the meaning of maximal? Maximal. An ideal is not equal to R in a ring that means M is not equal to R means M is a proper ideal. Will be maximal will be maximum ideal if there exists I is an ideal of R such that M is subset of I, where M is the then M is equal to I, or we can say R is equal to I. It may we say that it is impossible that may not there must be not any ideal between R and I. To find another ideal between mean, okay. Let example we take. Let R be the ring of integer and M is equal to 6i. So 6i means Mi is equal to the element of M is minus 12 minus 6 0 6 12. This type minus infinity to infinity and which are the multiply by 6. And but this is not this is not maximal average because vi the element we take t, the element is like minus 6 minus 3 0 3. Here t contain, so we can write like that m contain in t contain in r. So there exists an ideal which contains m between the r and m. So m is not maximal ideal. So t, if we discuss about t, there is no other ideal between T and R which contains these elements. Okay. So so region is n maximum. Maximum. Similarly, if we can say 5z, the element of 5z we take is equal to m. The element of m are minus 10, minus 5, 0, 5. So there is no other, we cannot find any other ideal which contain M. So direct M is a subset of R. So M is maximum. By two examples, we see that 2z, 3z, 5z are maximal ideal. So we can say that that the ideal, so the ideal prime ideal are always maximal. So we can say that M is maximal N. So this is we can conclude that if ideal is prime ideal made by the prime number or generated by the prime number, then this ideal will be maximal. This is important remark also. Now we take a theorem on basis of these. An ideal of a ring maximal if it is generated by some prime integer. If it is generated by some prime integer, that means prime ideal. Or this is already we conclude by the example. But now here we have to prove that an ideal of a ring of integer is maximal if it is generated by prime ideal. So, so, so here we prove let z plus dot be a ring of integer. Let be a ring of integer and s be the ideal of z plus dot. Actually, we have taken a ring Z plus and take a ideal S. We know that we know that ring of integer is principal ideal domain because it's generated by one principal ideal domain. So each ideal be the principal ideal and generated by single element. Now first we take first we take as be an ideal. Right, and generated by generated by prime element. So S is generated by P. Here P is the prime number or minus P. Or we take one P and we can take only positive, so it will be also proof for negative also. So we will show that S will so we will show maximal item. Now we assume that S just be that is now we will show or we have to show. Actually, for show that we assume a ideal S of a Z, and here we will prove that it will be maximal ideal. So we take that S is generated by a prime number because we have to show that a prime ideal is always a maximal ideal. So we take another ideal S dash which are lying between S and Z. So we will show that S is equal to S dash or S dash is equal to Z. Okay. So so let's take let we take S dash is also generated by Q. Here we not that Q is a prime number. Okay. So S belongs to S dash. So P is also belongs to P. Generation by P is also subset of Q. That means P belongs to P. That's why P belongs to because P generation of P, the set of generated by P is a subset of Q and P belongs to generation by P set. So P also belongs to generation by Q set. Okay. Then we can write here S dash generated by Q or S dash so P is the subset of this. P belongs to P generation by P subset set and P is belongs to Q because P generation set is belongs to. So then we can write P is equal to N. It means we find P is composite. If P belongs to Q, then P can be write in the form of Q. So P is equal to NQ. So that means P is composite, but this is converse. This is contradiction because we assume that P is a prime number. But this is contradiction that P is prime. So n is equal to 1 or q is equal to 1. So we can say that one of them n and q is 1. If n is equal to 1, then p is equal to q. Then p is equal to q. P is equal to q. Or if q is equal to 1, p is equal to 1. Now, now if p is equal to q, p generation by, so f is equal to x. Okay, because p generation set is equal to the q generation set. The q generation set is x. Now, when n is equal to 1, then we get p is equal to q. That means that s is equal to s dash. Now we have to find out when the case second and q is equal to 1. When we take q is equal to 1. Now is equal to 1. And we know the set of integer is generated by 1. So this is become our ring R. That means we can say that S generated by P set is S and this is by R. So our ring R. So if S is generated by P, then now second converse of this theorem. Now converse of now conversely we take S is maximal ID which generate by P. Here pH prime. Let pH not prime. If we assume that P is not prime. Okay. First we in this theorem, first we prove that P is prime, then we will show that P as ideal is the maximum ideal. Now we will show that S is a maximum ideal then generated by a prime number is maximum ideal, then it generated by prime ideal, prime number. So let P is equal to AB, composite number we assume, then P is generated by where A, B are both are not. Now P generated by this, so P is a subset of A or subset of 1. Okay, and P, so this is the set S, which is the subset S. This R from generated by P set is S, generated by A set we assume S dash we take S, and generated by 1 is we know R is your Z. So, so S is, so there we find an ideal which contain S and between the S and R, so S is not, so S is not maximal ideal. But this is contradiction of our assumption. We have given that S is a maximal ideal, not maximal ideal. Now just one direction. Now by one P is equal to A or A is equal, because it is given that it is a maximum ideal. So in this case, so in this case, A divide P and P divide P. That means A is equal to NP, and we know that P is equal to AB we assume. So and this cancel, we get 1 is equal to NB. That means implies N is equal to 1 and B is equal to 1. Because this is an integer, so the multiplication of two integers is 1 only when both are 1. Okay, here we take again, I explain you again concept. In this theorem, converse theorem, we assume that S is maximal ideal. So we will show that P is prime. Okay, and S is a generated by P and P is prime. Let P is not prime. If it is not prime, then it is composite number. So P can be write as this form, and that means P is a subset of generated by A, and this is a subset of 1. So S is a subset of S dash or this R. S is not maximal ideal. S is not maximal ideal. Now from 1, P, generated by P is equal to A or A is equal to 1. So A divides P and P divides A. So A we take NP. Okay. Here the multiplication and we know that P is equal to we have P is equal to A. So we put the value of P to divide and the product of two integer is 1, that means n is equal to 1 and b is equal to 1. That is contradiction because we have taken that P is composite. But this is contradiction. Contradiction because we have taken that that P is composite. P is composite. So our assumption is wrong. And it- that means we can say that if an ideal is maximal, then it is prime ideal. Or if a ideal is prime, then it is maximal ideal. So both sufficient and necessary conditions are here. Then a ideal is prime ideal, then it is maximal ideal. Okay, and a maximal ideal is always a prime ideal. So both that show that SP maximal ideal of that generated by P, then P is a prime ideal. So, so we can say that show if S be maximal ideal. So S be maximal ideal, maximal ideal of Z generated by P, then P be the maximum है, then it is P. Again, I explain this theorem again. An ideal of ring of integer is maximal if it is generated by some prime integer. So let first we take that a prime ideal will be maximal ideal. Ring of integer and as the ideal we generate principal ideal number. First we take as is ideal, okay, and generated by a prime number. And there is another ideal as which contains S. So S fully contains the S element P can be written as a composite of this. This is our P. P is the element of generator of Q. So P can be NQ. This is our composite number, but this is contradiction that we assume that P is a prime. It is given that P is prime. So N is equal to 1 and or Q is equal to 1. When it is Q is equal to 1, When it is P is equal, n is equal to 1, then we get P is equal to Q. Means P generated and Q generated are same. So S is equal to S2. Now, if Q is equal to 1, then generated P is equal to generated by 1. So this is R. So S is equal to R. So S is generated by P. Then S be a maximal address. S be maximal address. Now conversely we say the S is a maximal address. Now we assume that P is not prime. P is not prime, we take is a composite. If it is composite, then P generated by P a subset of generated by A. That means there is also a subset between S and R. So this is contradicts to our assumption. So it is not the prime. This is not a maximal adder. So we can conclude that if a ideal is maximal, then it is prime, and if it is prime, then it is maximal. तो स्टूडेंट आई होप ये थ्योरम आपको समझ आई होगी. इट इज वेरी गुड थ्योरम टू अंडरस्टैंड. दिस स्टेटमेंट इज वेरी क्लियर दैट if Z is a ring of integer, then the ideal S is called the maximal ideal if it is prime ideal. If or prime ideal is always maximal ideal. So both are the true sentence. Now we move to our Q. Our Q, which is the maximum ideal of Z plus? Which is the maximum ideal? So I told you that the prime number generated ideal is always maximal ideal. So 2Z plus. Here 2 is a prime number, and between 2Z and Z there is no other ideal which contains 2Z elements. So 2Z is maximal ideal. This is right. Now B. If we discuss about B. So then B is also a maximal ideal because 3 is the prime number, and the prime ideal is always maximal ideal. There is no other subset between R and 3Z, Z and 3Z which contain the element of 3Z. Okay. So 3Z is also a maximal ideal. But see Z6. Sorry, here 6Z. We can write here 6Z. 6Z. So 6Z we will discuss that this is not is a composite number. By 2 into 3 we can write. So element of 6Z contains by 2Z also and 3Z also. Okay. So the element of 6Z contains in 2Z and 3Z. So between Z and 6Z there are two ideals which contain the 6Z element. So this is not a maximal ideal. But simply we can say this is not a prime number or prime ideal, so this is not a maximal ideal. So C is the wrong option and D is also wrong. So two options are the right here, A and B. Which is true here? Here I told you that multi option are right. Which is true? Prime ideal is maximal ideal is prime ideal. Both are the right option because prime ideal, A ideal is maximal, then it is prime ideal, and prime ideal is a maximal ideal. So both in the theorem, just we have proved that theorem. Which statement is not true? Intersection of family of ideal is ideal, right? Z plus B a integral domain. Integral domain and Z plus 2 is a field. Z plus is integral domain. This is the integral domain, that's right, because it has not zero divisor. Yes, Z plus is the integral domain, right? Intersection of family of ideal is an ideal. This is right. Z plus 2, 0 and 1. This is a field because it has the inverse element of itself. So this is a field also. And non, all are the true. So non is the, I think, wrong. So coming to ring with unity is called integral domain. So Z plus is not have the, it has the unity also. So B is, I have confused. B is the right option. Right. All options are true because Z plus dot is also integral domain. Okay. If it is given 2Z, 3Z, 4Z, then we can discuss this is wrong. Z 2 plus, if ZP is prime, P is the prime, then it is filled because it has no ideal other than itself and identity. So three options are right. So fourth option non is not true. Which statement is true? Z plus is a CRU. That's right. Z plus is a CRU. The ring has no zero divisor, and Q plus is a field. Q plus is a field. Also. All are true. That's right. All are true. Which statement is true? Every ideal follow the cancellation law. That's right. Every set of all f0 is equal to 0 in ideal बिल्कुल सही. If the image of 0 is all the set, when we put 0 it gives a 0, then it is an ideal. Everything is an integral domain. Everything is an integral domain. No, it is not right because a ring with CRU, CMA community ring with unity, it's called the integral domain if it is without zero divisor. Finite integral domain is a field. बिल्कुल सही. Then we can say there are three options are A, B, and D. Only C option are actually there. This is the pattern of the Ethernet. So I put some question to solve you, uh, where you make confusion, more confusion. So I give you multi option, right option, multi option. Uh, there are right and have to select all right options. So okay student, thank you very much. Watch this video. Thank you very much.